Fantastic. And thank you very much.
Thank you for the introduction. Wow, this works. Yeah. My name is Juan Pablo. I'm coming from the University of Technology at Eindhoven. And I'm going to talk, as well described by David, about simulation and optimization methods to enable or to make faster the transition from diesel to battery electric heavy-duty trucks. I have a lot of slides, so I might have to run very fast through some of them, but let's see how we do with time. So we have already been through this a couple of times, but the Netherlands is no exception in the very ambitious emission goals that it has for the transportation sector. One of the policies that are being enabled is the implementation of zero emission zones, which will be taking place from 2025 to 39, the biggest cities in the Netherlands, which is basically almost every city. And that's a pretty complicated situation for retailers such as Albert Heijn, which is a type of Dutch Costco, Dutch Tesco, who, of course, they have to keep on doing all their deliveries, and with the zero emission zones, they have to find alternatives fast. So the challenges that they have, in spite of this pressure and incentive, is, can they actually still fulfill their current operations? What's the reliability of them? There's not many chargers out there. Public infrastructure is not readily available for chargers. So will they even be able to charge these trucks? Can their local grids support the charging of trucks? And then they also don't want to lock into a technology that might later show to be not the optimal one. So all these challenges sort of keep pulling them back from actually moving forward with investments. And the key questions that we want to address from our point of view is giving them the answer of what is the optimal charging infrastructure you need for your operations. Right? What is the number of chargers? Is it going to be 10 or 30? Are they going to be 50 kilowatt, 150, 500 or a megawatt charger? What do you need? And what is that going to have as an impact on the total power that is demanded at the site, right? Also checking if these new vehicles are compatible with their schedules that they already have, how much the transition is going to cost, and how reliable the different solutions are in the long term. So that is sort of our focus. This has already been looked at in the literature from various approaches. Some focus more on the electric or the power infrastructure, and some focus more on the transportation side of the infrastructure. And then they vary in methodology. Some are like bottom-up, trying to optimize everything together, and some are looking top-down into the macro level, possible locations for the chargers, and trying to see where it would be most beneficial to locate them. Also depends if it's on a micro analysis level or a more macro on national flows analysis. But yeah, those are the types of research that you can find. And we strive to find practical and explainable models that are using the already optimized itineraries that these retailers have right now to fulfill their ongoing schedules. So how can we sort of streamline those so that they are also usable with battery electric trucks, and giving them the chance to test what-if scenarios for the long term? Our methodology takes an initial data set that is more focused on the retailer demand data and switch it into a truck-oriented data set. Then we put that into the optimization module, and then we simulate this to test different conditions. Very quick view on the data that we have for the trucks. We have 3 types of trucks, different battery capacities expected, a consumption that actually varies with the payload and other conditions, but because of non-disclosure agreements in the middle, we just present as an equation of the form, linear depending on the weight. We have an average payload that is being delivered by these trucks, standard deviation. Typical round trip distance is within the range that can be done with these trucks. So doesn't go beyond 100 kilometers, so feasible, and about 150 tracks for the study case we're looking at. Departures and arrivals, we have them all throughout the day, no rest for the truck drivers here. It depends a little bit on which day of the week it is, but yeah, the departures take off a little bit after 6 a.m., but 24/7 activities. And the area we're looking at is the north of the Netherlands. There's 300 approximately locations. 27 tons are delivered to each one daily on average. And that main distribution center in red in the middle, which I am not going to give away which one it is, but if you're from the Netherlands, you might pretty much sort out what I'm talking about. For the optimization part, we have to define the sets and the elements that we'll be iterating on. We're going to have the set of trucks that we have, the set of possible origins and destinations. We're going to have a set of charger types that we choose as possible. We're going to have a set of time loops because we have our continuous time arrow. We're going to split it into small bits. And for each bit, we're going to have an energy price or P. And that also depends a little bit on the type of charger, maybe also on the location. Right now, we're not doing that, but in the future, yes. And then we have a set of itineraries, which is basically the tours that have to be fulfilled by each truck, at which time they have to depart, which time they have to arrive, what is the payload, yeah, the total distance that they have to do, essentially describing all their activities, right? The decision variables that we're going to have, the decision whether to charge or not at a specific time slot, at a specific type of charger, in one of the trip legs of the truck. And then we're going to have a decision variable on the number of chargers that we're going to choose at each location and which type they're going to correspond to. Those are going to be our final results, let's say. And the constraint that we have, very fast. We can get the total consumption that we're going to have for a specific trip L, just having the distance and the consumption of the truck. We can also get the amount of energy that is going to be charged before doing a departure. And then we can write this equation, which says, okay, the energy at which I am going to arrive with is going to be consistent with the energy I departed, the state of charge I departed with, minus the consumption, plus whatever I chose to charge before doing the trip. Shouldn't go below 0, shouldn't go above the battery capacity. For the drawing of that, each L is each of the small legs of a whole trip, right? And we're checking that that is viable for each L. Then we also have the constraints on the available infrastructure. We have we need to have the total number of trucks charging at a specific slot is not more than whatever we decided is the infrastructure at that spot, right? So we have 5 chargers, there can't be more than 5 people charging at the same time there. We also have to restrict each truck not to be charging at multiple points at the same time. That would be cool, but it doesn't exist. The dual charging right now. Then we have the time constraints. We have to make sure that the time that we choose, we are going to charge. It's actually consistent with the departure time that we are going to set for the trucks. And we also have to be consistent with the current time windows that whenever we choose to depart, we actually can, when considering the time to travel to the next point, we are fulfilling the time window at the destination. And we introduce here the small parameter beta, which gives you a little bit more flexibility on the current time schedule. So we can be completely rigid and not allow any deviation from the current schedules. With beta, we give some minutes where we can allocate the charging activities in there and maybe probably make feasible our project, right? And get some savings from that. Then the cost functions that we have, essentially the total cost of charging, that depends on the charging decisions, the total cost of infrastructure, number of infrastructure, like the price of each charger that we decide to actually place, and the peak energy costs. There's actually a connection cost that you pay according to the maximum that you will be contracted in each month. And we take that into account by keeping the maximum peak value that is being charged at the central distribution center, and add this parameter alpha, which considers that this costs might actually be much greater in the future, or we can make it very hard, and in that way sort of relax a constraint of maximum peak power that we can actually draw at our site. So yeah, introducing those two parameters, alpha and beta, we're going to play with those during the simulation. And for the objective, we put together all the costs in one big objective. We want to minimize this subject to the constraints that we mentioned before. And this is going to give us jointly optimized the optimal schedules for charging and the optimal number of chargers for your distribution system. In a nutshell, pretty drawing. I thought the green was going to look worse, but you can see we are going to have in horizontal all our trucks, and we're going to check in the time axis their decisions to charge, what impact they have on the final power curve at the central DC. There's a staircase right there. Gonna pick better colors for these. Then we're actually going to run our simulation on 4 days. We're going to discretize the steps into 9 steps. We're going to have 5 types of chargers ranging from 60 to a megawatt charger. Then we're going to have 130 trucks, 300 locations. We can control how close to the optimal solution that we're going to be with the solution software that we're using. And we're going to change the extra time that we allow for the schedules between 10 to 30 minutes. And then we're going to think that we're going to take the face value of the current peak connection costs and propose that they can be maybe twice as much in the future. And then finally, we're actually going to contrast our optimal co-design with what has been already decided by some stakeholders in the project we're working with, of the charging infrastructure that they are planning or installing. We're going to contrast that with our results. And yeah, the result that we have is that for a higher peak penalization that leads to lower power chargers in general, it uses lower power chargers, sometimes a bit less, tighter schedule constraints, use more chargers with slightly higher powers. And the average that they're trying to represent is the type of infrastructure that is adopted by the co-design. It does not use megawatt charger, which was part of the plan. It says that instead we should use more 700 kilowatt chargers. It also uses much less 60 kilowatt chargers, so slow chargers are not necessary. Instead, it's using much more of the type 2 and type 4, which are 180 and 700 kilowatt chargers. So those are more profitable in this current scenario. Then, when you look at the power consumption curves, we take here an average the average per day, and we can see that with the less time slack for the operation, there is more power that is drawn from higher speed chargers. That gives you slightly more peaks. Also, with higher peak factors, then you have to reduce the peak charging power that is used because it's more expensive. And then you cannot align your charging times as well as you would like to do the troughs in the price of everything, right? So there's a trade-off there between what you lose in having big peaks and having to decrease your infrastructure, and how well you can actually align your charging times to lower prices. So there's a trade-off that is also shown with the rule-based design, but in this case, you cannot modify the infrastructure. So here they're forced to be using these megawatt chargers and the design that they primitive design. And for that, we end up having slightly more peaks, and the optimization algorithm, it tries to fit even better to the lower modes of energy price, but still you get quite higher peaks with this solution. If you do, of course,
There's 3 minutes.
here you go. Okay, so for the total costs, essentially it's the same trade-offs, but take a look at energy, that's the biggest chunk of your operational costs. We can also have for different parameters, the different geographical distribution of chargers. Here it's all concentrated in the central DC. This can move geographically. There's a strategy what's going on here, but yeah, that's computer work. And then into the agent-based simulation, just there's good reasons for us to adopt it here, especially because of the queuing at the chargers. But yeah, it's not straightforward why you would use it. It makes sense in our case, but sometimes no. I see it just used because, right? But it's good to ask why we use it. General overview of the different agents that we have here, trucks and distribution centers in the environment, essentially. The trucks are going to have the state charts. They also have some uncertainty in their behavior, a power consumption model embedded. The distribution centers are able to queue the trucks in their in different chargers. They have a simple communication protocol to let them know they should be moving faster or slower according to the current queue. You've seen this before, trucks moving, this is what the software looks like. And then we're going to have 4 experiments where we're going to either optimize both the infrastructure and the scheduling. So we're going to test all these different combinations and get some results. For the results where you do not optimize and just use a rule-based approach to the charging schedules, you see that you have a lot more mean time spent in charging because they don't charge exactly what is needed, but they actually go a little bit beyond because of the mode that they have. And you can see that there's a particular problem when you look at the mean time queuing. If you optimize the infrastructure but do not use optimized schedules, you can incur a drastic mean time queuing, waiting for a charger. So it's very important that you optimize both, or at least optimize the schedules. That's going to have much more impact in the long term. And then we define the trip failure probability falling below a certain threshold for the battery of a truck. And we can see that if you only use the optimized schedules, right, don't change your charging strategy, there's no control, then you can incur into some trip failure probability. There's also more variability in it. So you have to be careful and include some type of active control there. And the departures from schedule, again, in the green case, can be a little bit more dramatic if you're not optimizing actively what you the charging schedules. So brief conclusions, wrapping up. The energy side for the transition to battery electric trucks is really key. It's really going to make a difference, and it cannot be looked away from. I have 18 minutes here. Okay. And and it's also key in this optimization modules to actually then test with simulation what is going on, because if you lock in into a decision, you can see that operationally you might run into different problems. So I think this moving into the digital twin sort of simulation is very important to test the results of the decision. That's it, wrapped up. And I have to remind you all of the victory of Argentina in the World Cup still. And I'll keep doing it for the next couple of years. That's it.
Very good. Thank you very much.
Thank you. Totally unrelated.
Time for one question.
You mentioned you were varying the energy stuff by failure, simply also varying it by ambient temperature and weather conditions. You to be looking at kind of worst case scenario until freezing cold rain in December, or you find it generate that?
For this case, exactly not ambient temperature. There is the auxiliary cooling depending on the load in there, but not ambient temperature. I didn't exactly consider that in that one. No. But
that will affect the battery. In cold weather, you'll need to stop more often than the great battery costs. But in example.
Yeah.
Well, actually, this is very strong.
Yeah, there's multiple things that I think we can include, maybe not in the optimization, maybe in the optimization, but then in the simulation environment, it will also make sense. So yeah, that's a very good point.
Thank you very much. That's great.
Thank you.